Lesson 7.4, Evaluating Logarithms and Graphing Logarithmic Functions. Please take a moment to write the first set of directions. Sketch the graph of y equals 3 to the x power and its inverse. And then sketch a graph over on the right. Write the equation for the inverse function. Please just write that much of this page and then press play, and we'll go from there. To sketch the graph of y equals 3 to the x and its inverse, I'm first going to draw in the reflecting line y equals x. And that means it's going to go through 0, 0, 1, 1, 2, 2, and so on. It's going to go all the way up on that top right, and then on the other side on that bottom left. We're going to create that reflecting line. So try to draw that in on your paper and label it y equals x. All right, so to sketch the graph of y equals 3 to the x, this is an exponential function. I'm going to start off simply by picking numbers and plugging them in for x. And remember, because this is exponential, these numbers will go off of our graph pretty quickly. If we start with 0, 3 to the 0 power, we know, equals 1. 1, 3 to the first power equals 3. But 2, 3 squared, already goes all the way up to 9, which is completely off of our graph. If we go in the other direction, negative 1, 3 to the negative 1 power, that's a negative right there, would be 1 over 3 to the positive 1, or 1/3. And then if I go to negative 2, 3 to the negative 2 power would be 1 over 3 squared, or 1 over 9. Please plot these 5 coordinates and then sketch the curve for this exponential function. When you're done, your graph should look something like this, an exponential growth model. But now when we take a look at sketching the graph of the inverse, this is where it's important to have this table. Remember, for the inverse, we're just going to reverse those ordered pairs. We still have x and y in the same column, but we reverse the coordinates. So instead of 0, 1, we'll have 1, 0, and then 3, 1, and then 9, 2. But then we'll have 1/3, negative 1, and 1/9, negative 2. Now watch what happens when we plot these coordinates. 1, 0 is going to be over here on that right-hand side. 3, 1, and then 9, negative 2 just goes off my graph completely. But if I go just 1/3 to the right, I'm going to go down to negative 1. And then 1/9 is even closer. Whoa, those are a little bit off. Sorry about that. I'm going to fix this one quick so it looks a little bit more like it should. So negative 1/3, so maybe something like that. So now notice as we connect these dots, our boundary isn't going to be the x-axis anymore. It's going to be over on the y-axis. So now we're not going to cross over and have any negative x values. We'll come up like so, and then all of a sudden we curve pretty quickly over here to the right and go on to infinity on that right-hand side. So that would be our inverse graph. Down below it says write the equation for the inverse, which seems simple enough in theory. We know the steps. The first step is to substitute y for f of x. Well, we already have that. So we're just going to start with y equals 3 to the x power. But then step 2, switch x and y around. So then we get x equals 3 to the y power. And then step 3, solve for y. So try to solve for y once. We really can't divide by 3. That doesn't make sense because 3 is the base. And y is the exponent, so we can't take the root because then y would just go on the other side with x. So when I ask you to solve that equation in the middle for y, we can't do it. But we have the sketch of the graph on our coordinate system, so there should be some sort of equation that matches with it. So here we go. The inverse of an exponential function is called a logarithmic function. Literally using that word logarithm, or log for short, as a way to write the equation for that graph up above that was the inverse for the exponential function. Please pause the video and write out steps 1 through 3. Once you do that, press play, and then we'll go through filling in the blanks. When asked to write the inverse for the line y equals b to the x, notice b is the base for that equation. So up above, that just means b would equal 3. X is the exponent and y is the output on that left-hand side. The first thing you want to do is literally just flip the order from each side. I'm not changing any variables, but I'm going to write b to the x on the left and y on the right. Then we'll switch x and y just like we did up above. But here's where we can kind of take it to the next step to get y by itself. We're going to use the prefix log, that's our abbreviation for logarithm, and we're going to loop the equation. I know that sounds kind of strange to say, but we're going to loop the equation. So here's what I mean by that. We're going to start with log. So it's the logarithm, which means it's the inverse. What the base was for the exponential function now becomes a little sub-base in the logarithmic equation. Here's where the looping comes in. From that log b, we're going to loop it to the other side, and we're going to say of x. So notice right here, the log and the x are in the same row, but that b is like a sub-number. So instead of squaring a number where it's kind of a little bit higher, this is like a sub-number, which is a little bit lower. And then we set it equal to the exponent, which is voila, y. So now we got y by itself. Now notice this will only work as long as b doesn't equal 1. All right, so here's how this will work for that equation up above. The inverse for y equals 3 to the x power would be, so the first thing we're going to do is switch the order. The second thing we'll do is switch x and y. And then the third thing we'll do is we'll actually create that equation. We start with the prefix log. Now remember, the base was 3 in our original logarithmic, or in our original exponential, so our base is going to be that little sub 3 at the bottom of the logarithm. And this is where the looping comes in. We'll take the log base 3 of x and set it equal to y. So this is the actual inverse equation. If you want to write it in the proper order, left to right, we could just switch it around and have y on that left-hand side. Y equals log base 3 of x. That is the inverse to that exponential function up above. Please take a moment to write converting forms. In this section of the notes, we're just going to convert back and forth from exponential statements to logarithmic statements and vice versa. In that first set of directions, it says rewrite each exponential statement in logarithmic form. So we'll just do one of these at a time. We'll start with 2 to the third power equals 8. We know this is exponential because 3 is an exponent. And we know the base is 2 and our answer is 8. Now, if we want to convert it to logarithm form, that means we have to have that log in our answer. That's what that would indicate to us. So it's kind of like our step 3 up above, that looping process. Start with log as your prefix, and then recognize the base. In that exponential function, the base is 2. So that's that little sub number that we write. Now, log base 2, what are we taking the logarithm of? It's that 8 over on the right-hand side. And again, 8 is in the same row as that log. And what should this logarithm equal? It always equals that exponent on the left-hand side, which is 3. So you're literally just rewriting the inverse in logarithmic form. Log base 2 of 8 equals 3. Let's try the next one. Same idea. 4 to the 0 power equals 1. Our base is 4, the exponent is 0. If we want to take the inverse and write it in logarithmic form, log base 4 of 1 equals 0. And you're just rewriting. We're not solving, we're not trying to evaluate anything. We're just rewriting one statement to another. Now that last one, kind of the same idea. 16 to the 1/2 power equals 4. Well, that's true because 1/2 is the same as the square root, and the square root of 16 is 4. To write it in logarithmic form, we know our base is 16, that exponent is 1/2, log base 16, and then loop it, of 4, equals that exponent of 1/2. And that's literally just rewriting forms. All right, please take a moment to write this section out. Rewrite each logarithmic statement in exponential form. So now you don't want the log in this answer. So no log term in this answer. They all start with it though. In that first example, log base 3 of 81 equals 4. Can you see how that 3 is kind of written just a little bit smaller than the log? So that's the base of the logarithm. To convert it back to exponential form, we're still going to loop, so it's kind of a consistent process. Start with that little sub-base, because that's technically where the exponent base would be in exponential form. So we're going to start with that 3. Well, it needs an exponent, so this is where the looping comes in. 3 to the 4th power. And you guessed it, it's going to equal back to that 81. When we convert to exponential form, notice there's no log in our answer. And our answer is a true statement. 3 to the 4th power is 81. You try the next one. Log 1/2 of 32 equals -5. Can you pause and write that in exponential form? Try it and then press play when you're done. Did you get 1/2 to the -5th power equals 32? Well, if we think about the validity of that statement, 1/2 to the -5 power, a negative exponent, means we would take the reciprocal of our base. Now the base of 1/2 would be 2 over 1. And 2 to the 5th power is in fact 32. So it's an equivalent statement just written in a different form. Our last example, log base 8 of 1 equals 0. Again, that little sub number is how we're going to start. We're going to keep our exponential form with a base 8. The exponent is what's on that right-hand side to the 0 power. And we all know that answer should be true. 8 to the 0 power equals 1. Part of what you'll do in your homework is just practicing rewriting from one form to the other. When talking about types of logarithmic bases, you're going to have two options. One we call common logarithm and the other we call natural logarithm. Now a common logarithm is any number base. And that means we use the log prefix. If you don't have a logarithm or a logarithm base listed, like for example log of like 15, if there's no number listed right here, so the base is missing, what that means is that it defaults to automatically be base 10. So if you have a base 10 logarithm, you don't even have to write the 10. It's very similar to chapter 6. When we had the square root, we never wrote the index of 2. We just wrote the square root symbol. But we've seen up above that we can have a variety of different number bases. And anytime we do, that's just a common logarithm, and we include that base in part of our work. Now over on the right, it's going to look a little different. If you recall from lesson 7.3, we had a natural base, and that was base e. So it would be consistent that the natural logarithm is only base e. So you won't ever have a natural logarithm with any number base. It's only base e. And instead of writing log for logarithm, we use ln instead. So ln. And I write my L kind of loopy like that so that it doesn't look like in. So if you see on your calculator, it kind of looks like this. That's an L. So if that helps you kind of recognize that. So for example, if you see something like ln of 15, kind of like the last one, what that would indicate to you is that you know there's a little base there and it's always base e. We would never have anything else. So that means you never have to write it. So no matter what your ln is, you don't have to write base e because ln defaults it to only be base e. Let's take a look at some examples down below to determine what the base should be. And guess what? This is the last part of the video. Determine the base of each logarithmic term. So please write these down. log 100, log 232, ln 12, and then ln 5. Try your best on that second and fourth example to make those little sub numbers smaller than the rest of your writing. And then we'll just do one question at a time. In our first example, remember log is going to default to a common logarithm. That means your base has to be a number. So we look for that little sub number in between the log and the other big number. If it's not written, this is one of those values that defaults to base 10. Pretty simple. But in the example on the right, log with that little 2 of 32, note that that little sub number is going to be what your base is. So that's going to be base 2. If it's any base other than 10, you have to use something like maybe your power chart to kind of figure out the answer. But anything that is base 10 is calculator friendly. And I'll show you how to do that when we do the second part of our notes. But anything that's base 2, base 5, base 14, anything other than 10, we can't use our calculator just yet to kind of help figure that out. So we'll try some other things. All right, over on the right, we have ln, and that means natural logarithm. Again, remember, nothing should be written there because we know that ln is always base e. So if you're ever wondering what it could be, you only have one choice. It's always base e. So I threw that last example in there just to kind of see how we could navigate it. ln 3, 5. If you're using ln, that means you're using the natural logarithm rule. And you can't have base 3 as an option. So this is not possible. ln can't have base 3. Can't, oh boy, I forgot the word have, didn't I? Hang on, I'm just going to slide that over. All right, can't have, there we go, base 3, only base e. And I think we're going to stop there. That's plenty for the first part of 7.4.